Well, what I was going to talk about is this is something completely different. What I wanted to talk about briefly is a completely different kind of thing that we need to do at big computer centers, but also sociologically, and that is to do what I call competitive cooperation. So the example is this AGORA project, or AGORA. The person who proposed the name, Javier Agudis, says that this is from the Greek word for the meeting place in a Greek city-state. And don't I know that the final alpha has an accent on it, so it's AGORA. Anyway, it stands for Assembling Galaxies of Resolved Anatomy. As usual with this kind of thing, there were lots of names proposed, and we had several rounds of voting, and that was the name that was finally chosen. What's unusual about this project is that there's currently 10 different teams using different codes that are competing with each other to do good science. The science is simulating galaxies at high resolution. And what we want to do is work cooperatively to raise the whole level at which we're doing these computations, and also work cooperatively to compare the code outputs for 8 different simulation initial conditions, compare to each other, to fundamental physics, and to observation. So that's the goal, and the hope is that we'll succeed not only in improving the way all of us do the science, but also to help each of the different groups, by comparing with each other, understand the limitations of our current implementations and ways to work to improve them. It's a difficult task because inevitably we're all competing. We're writing competitive proposals to get funding, to get computer time, and of course we have to say how good what we're doing is compared to everybody else, and at the same time we want to cooperate and help each other understand what the issues are and improve them. My computer is still booting up, so I don't know why I did that. But anyway, what I wanted to do was just talk a little bit about the sociology. So one aspect of the sociology is that this particular project wouldn't have been possible without a number of elements that have just become available. Okay, well, anyway, so one of the things that's interesting is that we couldn't have done this without a number of different pieces of software that have just become available. So one of them is a code by Tom Abel and Oliver Hahn that generates initial conditions. And it generates the initial conditions for the dark matter So this is the first page of the website for our AGORA project. And as I say, the thing that makes this unusual is that we're cooperating and competing at the same time. So I showed this slide yesterday. This is basically the AGORA story. So Piero Madao and I are the leaders, along with Tom Abel, Nick Nedden, Roman Tessier, and Lucio Meyer from Zurich, and James Wadsley. And we're all senior people. The guy who's absolutely essential to make this whole thing work has been Ji-Hoon Kim, a grad student from Tom Abel's group who was a postdoc at Santa Cruz. His first postdoc was at Santa Cruz with Mark Krumholtz. But because he spent so much time on this project and not working on things that he was doing with Mark and others, I actually funded him with HiPACC funds for I think it ended up being 4 months of his postdoc. He won an Einstein Fellowship as well as a Caltech Fellowship. So he's now with Phil Hopkins at Caltech, but continuing, thank you, Phil, to support this project. And so we're generating initial conditions at 4 different masses at redshift 0, 10 to the 10, 11, 12, and 13 solar masses. So from a dwarf to a giant galaxy, each one generated twice, once with few mergers, once with many mergers. And in addition, there's a hand-built isolated spiral galaxy which we're using to test the feedback and other prescriptions so that we're happy with the way. The problem is that by the time these codes, starting from cosmological initial conditions, get down to redshift 1, could be many months. And to tune up the simulations so that they're doing what we want them to do, we're working on this. So there's 3 papers in progress now, one analyzing the initial conditions, running them at resolution of 100 parsecs or better, just with the dark matter. Another testing that all the codes are properly implementing the cooling prescription, which is this Grackle code, largely written by Britton Smith and Matt Turk. And the third is what am I losing track of? Oh yeah, that's right, the isolated spiral galaxy. So, and that's being led by Romain Tessier and Oscar Agertz. So we're trying to not only start with the same initial conditions, which other groups have done before, as I'll mention, but we're also trying as much as possible to use the same physics. So the same UV background, the same cooling, the same stellar IMF, the same supernova metal yields, and crucially, the same tool to compare all the simulations so they can be compared on equal footing, and that's YT. And without all of these, we couldn't have done this. And these tools are just becoming available now, which means that this is an absolutely state-of-the-art project. We are also going to be setting up, we're using YT as a front end for the Sunrise code, which takes into account the stellar evolution, so every star particle properly evolved with whatever code you like, Starburst 99 or Bourgeois-Charlot or whatever. Sunrise doesn't care, it's modular. But then the light traverses the galaxy through the gas, and the gas particles or cells all have metals, and that means that there's dust, which will both absorb and scatter, and the absorbed energy must be, of course, re-emitted, and Sunrise is capable of doing the re-emission self-consistently, and also the H2 regions are generated using mappings. So we can generate thousands of lines. So the earlier project that in some way inspired this project, because this was such a failure, was this project called Aquila, and that it was a failure is stated pretty clearly in the abstract. So this paper was published just a year and a half ago. The various runs, 13, differed in their various treatment, but they had the same initial conditions. However, that was the only thing they had in common. All the physics in each run was different and was not controlled. And most codes tend to produce an overly massive galaxy, smaller and less gas-rich than typical spirals, with a massive bulge and a declining rotation curve. Actually, they didn't none of them, not a single one, looked like any spiral galaxy. They also didn't look like any elliptical galaxy. They didn't look like any galaxy anybody's ever seen. They concluded that state-of-the-art simulations, their simulations were unfortunately not state-of-the-art, cannot yet uniquely predict the properties of the baryonic component of a galaxy, even when the assembly history is fully specified, in other words, the same initial condition. Developing feedback algorithms that can effectively regulate the mass without hindering the formation of high momentum stellar disks remains a challenge. So the problem was that the softening in every case was 500 parsecs or worse, except for the Ramses, which had 260 parsecs. So they were very low resolution. They were not resolving the regions where stars actually form. And most stars form in galactic disks, so realistic simulations should resolve this. The scale height of the Milky Way disk is about 100 parsecs, and we really want to resolve the giant molecular clouds, which means tens of parsecs. And as Philip Hopkins explained in his talk, the modern codes can do that. If you don't do that, you're not really addressing the issue of where the stars form and how they form. You're averaging over too large a volume. So these show examples of what went wrong. This is where the code should be in terms of the stellar mass to halo mass, and this is where the code should be in the Tully-Fisher relation. And of course the dark matter isn't going to be on the Tully-Fisher relation, but the codes weren't either. This shows the z component of the angular momentum divided by what you need to be circularly supported. And what you want is something like this, if you want to have a disk galaxy. This was the ERA simulation, which was published in 2011. And that had a smoothing of the gravity at 120 parsecs, but it had the gas treatment at about 12 parsecs. And that's the minimum. I mean, you have to do at least that well. And so it had a nice disk that was rotationally supported, and it had other components that were realistic. This was a typical example from Cecilia Scannapieco, who led this project, of what was happening in 2009. And all of these are basically like this. They've got this very large amount of the mass, the stellar mass, which is not rotationally supported, with a little bit of the disk. And none of these look realistic. They don't look like any galaxy you've ever seen. So we don't want to make that kind of mistake. And the crucial thing is you first of all have to have resolution that's much better than this. If you don't have that, you're dead. But then we also want to have a much better control over the gas physics, the star formation, etc., so that we're much closer to being realistic. So these were the goals. And in addition to setting up the right initial conditions, the crucial thing was to maintain the collaboration both by in-person meetings, which we've had every summer in Santa Cruz, and we'll have another one this August, and every few months a telecon, and also, especially thanks to Jihyun, keeping the web page up to date, and then sometimes blasts of emails. There's one going on right now having to do with getting the Grackle code to work well with all the different, the 10 different simulation codes. So as I said before, while I was waiting for my computer, the multi-scale initial condition generator, the background model, the Grackle code, several of the simulation codes, and the YT code, and also this ability to generate the visualizations on the fly with the GPUs, are all quite new and are enabling technologies. So it's state-of-the-art. And the hope is all of these are publicly available. And the hope is that this is going to advance the whole field. Incidentally, at this point, according to Jihyun, we have 104 collaborators from 48 institutions in 8 countries. And we are open to further collaboration. And of course, since our initial conditions are completely public, people are free to run their codes and not cooperate, but we're going to try to make it so attractive that they want to. So the first paper has now been published in AppJ Supplement, and it describes the project. It includes, for example, this illustration of 9 of the 10 codes. The one code that has not yet produced these is Anatoly Klipin's art code. There's another version of art, the Kravtsev Chicago version, but Anatoly says that we will catch up, and so there'll actually be 10 and maybe more codes. These are exactly the same initial conditions run just with the dark matter. And you can see, if you look very carefully, that they're not all the same. Look at this region, for example, compared to this. And I think this is a weakness of Enzo, maybe.
Yes. We wrote a paper about that in 2005.
Okay. Okay. So, but okay, but look, the point, one of the things we don't want to do in this is gotchas. I mean, we don't want to cast aspersions on each other's codes. That's not the point. But what we do want to do is compare and allow each group to see what they're doing well and what they're doing not so well. So I'm showing these partly because all of these figures were generated using YT. So the point is that YT can read the output from every one of the codes and analyze them exactly in parallel. And that's critical if you want to do this kind of comparison project. Again, that's something that was not done at all in the Aquila project. And what we have all agreed to do is to store approximately 200 time steps and to, at the same scale factors or redshifts, including probably storing a bunch of additional ones at a few time steps, storing every single time step, not just the major ones. So that we can do very, very careful comparison to see exactly what's happening. And analyze them all just the same way so that we can do these kinds of careful comparisons. This is the squared density, and so what you're supposed to notice is, this little lump is either not there or a little differently placed, and of course these are the kind of timing things that always happen. So this is not a surprise, but it's something that we all need to be aware of. I quickly mentioned last time when I talked at the beginning yesterday that every month or two, Trudy Bell, former editor of Scientific American and IEEE Spectrum, who's won 20 major awards for science writing, she works for HiPACC as our senior writer, and she produces these astro shorts, we call them. And so one of her clever ideas for the astro short about the AGORA project, which came out last December, was to compare with the fable of the blind man and the elephant. The blind man studying the different parts of the elephant, but whose observational results are not consistent for the entire animal. Astrophysicists have been able to model only parts of the universe. The computer models have been inconsistent, but reproducibility is a fundamental principle of the scientific method, something we emphasized in the AGORA paper in APJ supplement. Only if a result from an experiment can be independently reproduced by other scientists can it be considered as robust. Now, a new ambitious multi-year project is figuring out how to reveal the entire element and also discern which of the inconsistencies are due to complexities of astrophysics versus computational issues. So, and of course, what we're also trying to do is some outreach, and we'll be doing this as the project goes on. This is one of the things I try to do in HiPACC. And I think it's critical as the simulation community, not just for simulations in galaxies or even all of astrophysics, but much more broadly. We have to explain, we have to do a good job of comparing our results with each other, with fundamental ideas, and with observations and experiments. And we also have to explain what we're doing so that people understand the nature of simulations becoming so important in science and also in public policy. So I want to regard this project as a prototype of how to do it right. This is the actual workspace, and this is where things actually start to get interesting. This is a wiki, and any member of the collaboration, all 104, can edit this. It's like any wiki, but of course we ask members to respect each other's contribution and restrain from invasive change. But there's space in here for all of the working groups. Here are the working groups. There's 4 working groups that are developing the infrastructure, including, of course, the YT one, which is led by Matt, but also 9 working groups that are looking at the different scientific aspects. And these working groups are almost all led by junior people. This is my last slide. Thanks to NERSC, we have 100 terabytes of workspace for the 10 AGORA simulation teams, so basically 10 terabytes per. Each group will do, let's say, 8 simulations. Let's round that up to 10. Store 200 time steps. Each time step is roughly 5 gigabytes, so that's 10 terabytes. Actually, the way you get this is you don't ask for so many terabytes, you ask for so many service units, and the 100 terabytes corresponds to enough service units to read and write several times. And I asked for that, and they gave me everything I asked for here at Originally, I'd hoped that we could do this on our small computer system at Santa Cruz, but my colleagues were very unhappy when I suggested having 100 outsiders have logins, whereas with 5,000 users here at NERSC, and also with no restriction to only American citizens, which is not the case in the NASA system, NERSC was a really great place to do this, and they've been extremely cooperative. And I also asked for 5 million CPU hours just to run YT and Sunrise, and they said sure. And what I'm hoping is that we'll get enough of these GPUs that we can do the on-the-fly visualizations from here also. We have 8 of these Kepler 20s at Santa Cruz, which we've been using to pump out the visualizations that Alex Bogert demonstrated yesterday. Apparently there's some problems here getting the team to agree to put in the more GPUs, but I'm hoping that that'll be resolved, and HiPACC can supply up to 10K of matching. You're going to help, Peter. Okay, good. So, and then I've already mentioned this, the science working groups are comparing to each other fundamental theory and observations, and a number of theorists like Mark Krumholtz are part of the AGORA project. It's not just the galaxy simulators. The steering committee is helping to keep the project focused on cooperation, getting quick results, and making our simulations widely available. Most of the working groups are led by young astrophysicists who are eager to write papers quickly, and I hope that it'll be a model for future efforts of competitive cooperation. Pardon? Okay, I hadn't heard that, but yes. But, you know, it's a hard thing to do, but it's important that we do it and that we do it right. And so I think that this is, I'm trying to make this a model of how to do it. So anyway, thanks for your attention, and thanks for everybody coming to this workshop. And I think it's time for lunch. Are there any questions before we break for lunch? I think we're just a few minutes late.
I have a question. So this is really the flagship Pioneer and Plan project. It's great that HiPACC led the way here. And I think it's something to really tout in the final report, that you're transforming the way science is getting done.
And we're making a lot of software publicly available. That's going to be very widely useful.
And this should be the way everything happens. But there's always this problem with sustainability of data. How long is NERSC willing to give you that?
Well, I raised, of course, when I wrote the proposal, I said we're going to want to keep the data publicly available at the level of at least 100 terabytes, and probably realistically it's going to double for a few years. And they said, well, they can't make any promises. Probably another year isn't going to be an issue, and after that, what can we pay? Now we have this petabyte system, courtesy of the Huawei company at Santa Cruz, most of which isn't spoken for. So we can host for at least a few years at Santa Cruz if necessary. Yeah. And of course the price of memory of storage is dropping so fast that I'm hoping this isn't going to be an issue.
To make this valuable, the compute has to be close to the data.
Yes, that's why the thing that's great about NERSC is that they're letting us have the storage and the compute capability. And so for the time being, this is where it's going to be. And as to what happens after that, I think we're going to have to, I don't think we're going to get any guarantees. Yeah, but as you said, Mike, to analyze, if you're going to look at outputs at the terabyte scale, you've got to have a pretty powerful HPC system. So you don't want to completely isolate the data from the computing.
And that's why our cloud is integrated into our HPC environment.
Right. Yeah. That's what you have to make this useful. So I think this is going to be useful as legacy output. A lot of people are going to want to look at it, and our aim is to make everything public ultimately.
Want it to be around for at least 5 years. That's my prediction.
Yeah, but we can't get anybody to guarantee that right now, and I don't think we need to.